Hello to everyone and welcome to very first video lesson about zone software in this year. And Happy New Year, by the way. I would like to represent three new options in zondres2d software, which mostly dealing with structured tensor. The first option is updated image-guided inversion. Let me start with example. Here is some ERT dataset plus background image from GPR survey. So this is not easy type of images because it contains much more details than they can resolve this ERT. So structured tensor algorithm involved in image-guided inversion. First of all, I would say about images. There is two types of images. First of all is seismic or GPR images, which contains a lot of details, and they needs required in structured tensor algorithm to analyze this type of images. And second one is a different kind of sketches. Sketch is much better, especially if they fit to model mesh. So if boundaries on this sketch the same like mesh, you can see here. Another thing, better to use grayscale images. Because anyway, any colored images will be converted to grayscale, but by default algorithms. So you do not control contrast between boundaries, and for example, green and blue sometimes gives the same gray shade. So you should control it. Anyway, this kind of inversion, based on structure tensor, they are special model which allow you to make some preparation of image. You can find it right here in background image options editor. So here is some filtering options which allow you to mark some important significant details and suppress details we don't. For example, in this picture we need only these two borders, and there is a lot of options, and I think it's reward separate lessons for this window, but I show just one options. This is anisotropic smoothing, and it's help you to improve these two details, significant details, and suppress some small and not important details. So let's apply this procedure, and you can see that image looks much better, not so many details. And after that, we can save this result and repeat this operation to maybe make it better. Okay, this is enough. So of course, here is a lot of them, but we apply just this one. After this, we can just apply this image, use this image for image-guided inversion. So now we can see picture is significantly different. Okay, now to turn off background image inversion, we should use these options. And if it's image guided inversions, EGI settings show it up. But for this type of image, we need this setting, just structure tensor without any force. Because for sketches, I will show you how to apply force. So some additional criteria. Also, it's only depends on smoothness. So smoothness, flatness matrix will be rebuilt based on image. So smoothing factor is met here. So let's see what we can do here. So as you can see during inversion, our result model trying to fit in basic boundaries on this image. So here is two strong boundaries and very good fitted now. Let's see how it looks like in contours. Yes, it's pretty good fitting to this image. Okay, but this type of images as image guided, they not perfect. As I said, we have a lot of details. Perfect image is sketch in grayscale. Let me try to import another one, which I prepared in advance. It's not necessary to have black and white. It's maybe another grayscale image. And let's see what we can do with this type of image. And you can see it's fitted up in mesh, but it's not necessary. So it's maybe some slopes and everything. It's not necessary. This is just a perfect image. Let's see how it looks like with structure tensor. Let's take a time for large images to process this picture to construct operation. Well, it looks very good. But this kind of images, they can apply brute force in IGI settings. Yeah, we can use, for example, three type of structure units. It's maybe tensors, it's maybe gradients built by images, and averaged blocks. Plus, we can use two additional golf function. It's maybe correlation between two images or gradient. So it's like for regular trend inversion. Let's choose gradients here and averaged blocks. Okay. So result will be pretty similar, but this goal function has a big pressure on inversion and trying to fit all blocks structure in the image. So you can try different options and it will give a little different results. So it's now not only smoothness works, but also gradients, trying to minimize gradient between image and model. Okay, I think this is even a little better. It fits perfectly to our sketch. And so we can use some different type of settings for this kind of image guided inversion. So it's different combination, different criteria, and we can see a little improvements with it. Okay. Now let's check another example. This is more deep and with seismic. Here is a lot of details. It's much more than we can resolve here. And I don't want even process this image and prepare. I will do it with what I have because I don't know which details are significant, which are not, because here is a lot of them. So let's go to EGR settings. And here we don't need any force because it will work maybe sometimes opposite to structure tensors. And we use only smoothness here. Let's see. It's a very big image, so it's maybe process it a little longer. Well, it's not bad because model fits in most of significant details of this image. Of course, it's a lot more, but it couldn't be fitted in it because it's too many of them. Well, I think this is enough. You can see also these near surface details in light blue are showed up here. So this is not bad result for such detailed image. Okay, we finished this first options, and I'm going to show you next one. This is another type of joint inversion they recently added. It's based on shared smoothness between two parameters. This is our data set. I usually show joint inversion, and it doesn't use this type of joint inversion. It doesn't use some specific goal function additional. It's use only smoothness. So only flatness matrix is involved in this kind of joint inversion. So it's maybe not so similar results, not so high correlation sometimes, but it is absolutely independent method. So I think the reason of adding more joint inversion criteria to compare it, and if two or three of criteria is has a good correlation, that means this model can be trusted. So this one here is pushing factor doesn't matter, and only smoothness as a deal. Again, and let's me open seismic model. It's some old model, but we anyway will start with just a gradient, and we'll see how model changed from iteration to iteration. So it's also based on structure tensors, but it's use structure tensors of one model for another and in opposite way. So this is because we had a start gradient for seismic. Now you see all these details of this start gradients. But it will disappear after few iterations. This kind of inversion needs more iteration to make models looks similar. and it depends on smoothness settings. So we will wait till inversion finished. Now you can see already some details thinner because we compare smoothnesses. This is the thing of smoothness is that uh, gradient, if we have a gradient correspond to flatness matrix build it's a zero. But if we have no gradient in model, it's also zero. So sometimes we will not see some borders on another section that we see on a section. But maybe it's a good, so it's maybe pro and contras about it. Because in real geology we can have or have not some borders for some petrophysical parameter. From my experience, this method is better for some global details of section. Let's see how it looks like in contours. Well, it's not bad. So we have all this massive part the same, just here is some another details, but gradient should be the same. So you can see here gradient and here gradient. So some global details is pretty similar. So as alternative to another methods, you can try this for your couplet data sets. So we finished this example, and I'm going to show last options for today, last new options. This is adaptive smoothness. We also used structure tensor of model for this, and maybe you recognize this as some example Blue Ridge from collection of local files, that example. And what is goal of these options? It's trying to make model more structured, so there is not a lot of small targets on sections, but it's trying to join it to one more bigger structure. So results are more structured, and sometimes it's help to avoid of overfitting. So these options you can find right here in smoothness. Use adaptive smoothness. The thing is that final misfits for data is not so good, like for not using this type of restriction, a structured type. But model always look better, so we can see not so many details, especially in deep part. So this flatness matrix is adapting to model, to current model, and sometimes it's good, sometimes it's not, especially if we have a problem with some layers has a breaks because of some surface heterogeneity. Sometimes it helps to make our model is more structured or layered. For example, this is what we have here. And for example, we can use L-curve criteria, which sometimes lead us to overfitting. And here we have not overfitting with it. We'll have pretty same model because our flatness matrix are stabilized by structure tensor. So it's pretty similar, and we can see all slopes of structure. Now let's me keep it in a buffer. And I'll try to make inversion without this criteria. Let's see what we will have here. It should be a little different. Okay. Yes, it's similar, but some details are different. Of course, here is different gradient and endless. So this is actually questionable options, but you can try this one. Okay. Thank you very much for your attention, and see you next time on next video lesson.